Alrighty. I didn't have a chance to type up stuff. I did IPI today, so we're just going to go back and forth. Make sure that you have the problems up next to you so that you know how to do this. So first I got to make sure I have my calculator up. Okay. So one of the ironic things that is I was looking at my old notes, and it says, we will not be doing any calculations involving freezing point depression, although you should read it. So you needed to understand it, but not do anything. So for me, personally, I've never had to do any of these problems. I think we just skipped over chapter 11. So this is my first time doing all these problems. So I will be skipping number 5 because that problem, I have done it forwards and backwards, but I have gotten 2 different answers. So there's something wrong with my method. However, so I don't want to teach you the wrong way to do it, because I was trying to double check to see if I knew all this stuff. So we're going to start on the first one. First one is an isotonic sodium chloride solution contains 0.9% weight per volume sodium chloride. If the E-value of boric acid is 0.52 equivalents of sodium chloride, so calculate the percentage strength weight per volume of an isotonic solution of boric acid. So let's do blue. All right, number 1. So we're going to make an isotonic solution for, if it was weight per, I think it's weight per volume that they want. Yeah, okay. So this would be our 0.9%. So NaCl. And so changing it to boric acid, you take, this is now sodium chloride, and now the equivalent of taking that to boric acid, you need to look this up in the E-values list in your book. Or you can pull up an MSDS page and find them. So this one, you just take 0.9 grams and divide it by 0.52, which is the ratio of sodium chloride to boric acid. So you find that that is 1.73. So the equivalent would be 1.73% to your 0.9% NaCl. And so this is boric acid. Ugh. All right. Let's go to the next one. Insert some space. All right. So number 2. Sodium chloride is a 2-ion electrolyte dissociating at 90% in a certain concentration. Calculate A, its dissociation factor, and B, the freezing point of a molal solution. So molal means like 1 molar. So that is the first thing that most people do not know when they're referring to molal, and how that deals with your freezing point and stuff. So first thing is, let's do 2A. Why is nothing working today? All right, 2A. So we have to figure out our dissociation constant. If it is dissociating at 90%. So why do you need to know this? Well, so for every single particle on the side, so like every single particle will draw water. So if something disassociates more, it will draw more water. That's essentially the main thing. So that's 1, this will be 0.9, this will be 0.9. Because this is 90% disassociating, that is also 90%, but then there's still 10% that hasn't disassociated. You need to add all these together so that you find that is 1.9 disassociation. So that is your I value, I believe. So that is your first number for A. And then for B, the freezing point of a molal solution. So for the temperature change, the freezing point change is equal to the constant freezing point times molality. So your Kf, your constant, is 1.86 centigrade per molality. So for this, for 1 molar, you're going to have 1.9. So you're going to have, so this is per B, sorry. 1 times 1.9, that equals 1.9. Molality. And then you're going to multiply that. And this is a freezing point depression, so it's technically negative. So it's negative 1.86 times 1.9. And so that will be negative 3.534 degrees Celsius that will be depressed by 1 molar molality of sodium chloride that disassociates at 90%. And this will hold pretty much true for anything that disassociates at 90%. So if you run into this again, then you don't need to do too much. All right, let me insert more space. Come on. Sorry, we're struggle busing today. Okay, so number 3. Okay. A solution of anhydrous dextrose, molecular weight 180, contains 25 grams in 500 milliliters of water. Calculate the freezing point of the solution. So we have to find, we're going to use the same equation that we used up there. So we're going to use this equation, temperature depression equals constant times molality. I don't like putting M because I do moles all the time and I end up, and then your Kf is equal to negative 1.86. Okay. So some people don't remember what their molality is anymore. So your molality is your moles of solute over your kilogram of solvent. Okay, so if you don't remember what that is what that is. So I'm reading my notes because I did this a couple days ago. I've been piecing this together because I haven't had that much time to sit down and just do it in one big go. So we have 25 grams of dextrose. And we're going to change it to 1 mole dextrose. And so our molecular weight was 180 dextrose. So then we find that that is 0.139 moles dextrose. So we have to find the molality, and we have 500 milliliters, which is half a liter. So that's the same as kilograms. Liters to kilograms is a 1-to-1. So your molality is 0.139 mole divided by half a liter. And so you find that that is 0.278 molal. And then you have to plug and chug into your equation. So this equation up here. So it would be your change in temperature is equal to 1.86 times 0.278 molal, and that is equal to negative 0.517 degrees centigrade. Okay. Oh, fun, we have more. There's a lot of problems today. One of them is my want to do this. Okay. All right. So to read the question. Procaine hydrochloride with a molecular weight of 273 is a 2-ion electrolyte dissociating 80% at a certain concentration. So we first have to calculate its dissociation factor, then we have to find its E value, and then we have to find the freezing point of a molal solution of procaine hydrochloride. So let's do this, people. All right, so first off, your procaine chloride will dissociate into procaine and chloride. Very simple. And so it's an 80%, so this would be 20, this would be 80, and this would be 80. And then you add them together to find the dissociation, which is 1.8. Then you want to figure out the E value. So your E value is the equivalent. So in the previous problem, it said that sodium chloride dissociates at 1.9. It does not. Its I value, if you look it up in the table, is 1.8. So you take 58, which is 0.5 grams, times 1.8. This is all for sodium chloride. So this is sodium chloride's molecular weight, and this is sodium chloride's I value. And then you take procaine, which is 273, times the I value that we found up there. And then you will find that the I value is 0.21. So there's your I value. Then you have to find the freezing point depression for 1 molal. Well, in the previous one, we had half a, basically, well, so 1 molal would be over 1,000 liters. You would just take the disassociating content. So it would be 1 times 1.8. So you get 1.8. So that's just your molal of that. But then you have to multiply it to find the change in TF is negative 1.86 degrees centigrade per molal times our molal that we found up there. And so you're going to find that your freezing point depression is 3.348 degrees Celsius. Okie doke. I gotta add more space. I need space. Space. Okay. All right, we're skipping 5. I'll explain. I explained. I don't like number 5. Also, number 5 is not something you're going to see on an exam. If anybody gives you that on an exam, they ought to shoot them. So just don't believe in it. All right, so 6. All right. All right, the freezing point of a 5% solution of boric acid is negative 1.55 degrees Celsius. How many grams of boric acid should be used in preparing 1,000 milliliters of an isotonic solution? So, the freezing point depression of an isotonic solution is negative 0.52 degrees Celsius. And so we know that this one is 1.55 degrees Celsius. But what we want to find the grams of that we need to add, and then we also need to know how many grams are in our 5% solution. So finding the amount of grams is 5 over 100 times, what is they wanted 1,000? Yeah, they wanted 1,000 milliliters. So 1,000. So then you find out that this 5% solution contains 50 grams. So then you cross multiply. So 0.52 times 50. And then divide by 1.55. That's not right. Oh, because it's 0.2. Never mind. All right, 50 times 0.52. All right, divided by 1.55. There, yeah. So it's 16.77. So 16.77 grams. See, and that's how you find that one. Ooh, we don't have to insert any space. Okay, let me see what the next one is. All right, 7. So for 7, I like to rewrite what you would call the prescription, but prescription is what is dictated. That is literally what it means in Latin, is the dictate of the doctor. But I like to call this a recipe. Really, it's just cooking. So this is ephedrine sulfate. We're going to put 0.3 grams in it. We're going to add sodium chloride QS, which means 2 however much we need, and purified water. And this person has said, make it an isotonic solution, and then tell the patient to use it as directed. So how many milligrams of sodium chloride should be used in compounding this prescription? So with ephedrine sulfate, we need ephedrine sulfate, and they want 0.3 grams, and then they want NaCl QS, and then they want water to 30 milliliters. So let's first figure out how much sodium will we need to make this isotonic. So for that, you would need to multiply the amount percent times 30 mLs, and you'll find that that is 0.27 grams will need to be put in into 30 milliliters to get it to be isotonic. So we need to find the equivalence of sodium so that we can figure out how much sodium we need to do. So we have our ephedrine sulfate, and the equivalence in the table in the book is 0.23 E, so you know it's sodium equivalence. So the equivalent amount to have is 0.069 grams NaCl equivalents. So this is the amount of drawing power of the particulates from the ephedrine sulfate as it equals sodium. So we know that the total amount to make it isotonic, and we know the amount that the ephedrine sulfate is going to pull. So now we need to figure out the remaining amount of sodium that we would need to add to meet that. So you would take from over here your 0.27 grams, you take away the amount of particulates you already have in there, and you find that that is 0.201 grams sodium chloride that you would need to add to get an isotonic, like, drawing power, essentially. So let me insert some more space so that we can do the next problem. All right, so our next one is diperphen hydrochloride, 0.5%, scopolamine, 1/3%, and sodium chloride to be made, and 30 milliliters as well. And we're told to make it isotonic, and it's for use in the eye. So scopolamine is an anticholinergic. It is used in all right, I'm trying to look at my notes. My notes don't make any sense today. Okay. So we're gonna try to figure this out. So diperphen hydrochloride, and they have 0.5%. So we're gonna make 30 mLs. So 30 ml times 0.5%. What did I multiply this by? Oh, I did this. Okay. I did this earlier. So half divided by 100. And I found that it was 0.15 grams of that we need. And then scopolamine, we need 1/3%. So that is 30 ml times 0.3333333, repeating, divided by 100 And that is equal to 0.09999. That's all repeating too. So then we have to find the equivalence of this. So the equivalence for division is 0.15 grams times its E value, which is 1.5. That's your E. And then you find that that is 0.0225 grams NaCl. And then your other one, scopolamine. So there's a fun thing about scopolamine is that it is known as a zombie drug. You can get it in people's. It's used by mafia and stuff for that. Yeah, it's interesting. So then you multiply that by its E value. You have every single thing has its own E value. Unfortunately, you have to learn how to do that. So with that one, you find that I just typed in 9s until I felt tired. So it was like 3 9s. So that's sodium chloride equivalence. And then you have to find out the amount of sodium chloride that you need for the solution. Well, the nice thing is back here at this one, we already found it out. So it's 0.27. So 0.27 grams for every 30 milliliters. And then you have to add up these two together. And you take it away because these are its pulling power away from, and you find out the amount of sodium that you need for the rest of it to make it isotonic. So why would you want to make something isotonic? Well, first off, this is going in somebody's eye. If I just dumped like a whole bunch of water in your eye, you would notice it. It would irritate your eye if anybody has ever tried to wash out their eye. If you use saline, it doesn't hurt as much. So that's one of the other things is that you can actually make somebody's disease state worse if you just dumped a whole bunch of drug directly into their eye. So that's the other reason why you guys should learn this. So all the other problems are very, very similar. I'll go through them all because I've done them all. But yeah, if you have problems with getting through a couple of these, just fast forward to wherever you need help. But the next one is number 9. Okay. All right, so we're going to have zinc sulfate, boric acid, and purified water. And then you have to add boric acid instead of sodium chloride this time. So what we're going to do is I'm going to write down how much we need of each thing. I'm going to write down a recipe to double check I have it. So boric acid, US, and then our water, 30 milliliters. So we already know, because of this one too, is that we need 0.27 grams of sodium chloride equivalent to get to that. So with this one, it's gonna be a little bit different. So we're gonna find we're going to take zinc sulfate and multiply it by its E value, which is 0.15 is its E value. And that is 0.009 grams sodium chloride equivalent. And then we're going to find the difference. So we're going to take 0.27 minus 0.009. So we figured out the drawing power of the one. So now we have to figure out the amount of sodium chloride equivalents that we would need. So we find that we need 0.261 grams sodium chloride equivalents, but this isn't boric acid. So how do we change it to boric acid? Well, the fun thing about the equivalents is that it is just a ratio. So it's kind of like specific gravity, but instead of the specific gravity is more of how much per volume, weight per volume. This is how much kind of pulling power per equivalent of sodium chloride. And this is something that's been left over since, God, probably since like the 1700s. So it's from the alchemical weights and measurements that we still have around. So boric acid, this is boric acid's E value. So this is the amount of equivalent boric acid it would take to the equivalent amount of sodium chloride. So there's a good way that you can think about this. So you can think about it like this: is that you have it kind of like for or no, it's maybe so it'd be like kind of like this. That's kind of your ratio. So then you find that this is equal to 0.5019 gram boric acid that you need. So it's just a conversion. It is just your normal conversion. It just doesn't. People seem to be getting caught up on that. It's just a conversion. Don't worry about it. I need to insert some more space. All right. Okay. So let's see the next problem. Next problem. All right. All right, so we're going to do dextrose anhydrous, 2.5% sodium chloride QS, and then we need 1,000 milliliters of sterile water for injection. And we want to make sure that this is isotonic, and we don't want to. Oh, sorry. Oh, I didn't realize it's 1 in the morning. Okay, so how many grams of sodium chloride should be used in preparing the solution? So when is dextrose a medicine? And a lot of people will go, well, it's just a sugar. So no. So this is a fun thing that you will learn, is that everything is a medicine. Everything can kill you. So technically everything is a drug. So dextrose can be a drug. Sugar can be a drug. Sodium chloride can be a drug. You can kill people with sodium chloride. It has happened before. You can kill people with dextrose. So we got to find the E value of dextrose, and the E value of dextrose is 0.18. That's its E value. All right. So we first have to find out how many grams do we need in our 1,000 milliliter. So, and multiply this by the percentage. All right, that's 25 grams. Then we have to find out its pulling power. So we have to multiply that by its E value. And that is 4.5 grams of sodium chloride equivalent. So that's its equivalent pulling power to sodium chloride. Then, so we know that the isotonic amount of sodium chloride is 0.9%. So then we have to figure out how much sodium chloride equivalent will we need, which is 9 grams. So then we need to take away the equivalent amount that we already have in there, which is 4.5. So then that leaves 4.5 grams sodium chloride to add. So why is this a nice even difference? So you have 4.5. This is exactly half, which might make you kind of curious as to why they would do this. This is actually a standard compounding formula. Like this is something that I wouldn't even. This is something that you can compound all the time. Not like super common. Like actually, I've never had to, but it is common enough that I have encountered it once. So it's if you take all the pharmacy students in the world at any time, and in the possibly amount of hours I've worked, times 300 million in the United States, it probably gets compounded about a couple times a day across the nation all the time. So it's not so uncommon that it's never done, but it is something that happens. So, all right, where are we? We are on 12, right? Yes, 12. So 12 is a sterile ophthalmic preparation, contains 6% bezofloxacin. Its E value is 0.08 in each 5 milliliters. Calculate the quantity of sodium chloride required for isotonicity. So, floxacin, I'm trying to remember what that is. So, we have to figure out we have 6% bezofloxacin. It's going to be in every 5 milliliters. So you find that is 0.03 grams bezofloxacin. Then we have to find the amount of sodium chloride. So this is the stuff that's already in there. So then we have to figure that out. That is 0.03 grams times its E value. And that is 0.0024 grams sodium chloride equivalent. The next one is figuring out how much sodium chloride should be in there. So then times that by 5 milliliter. That is our, and so then we find that that is 0.045, which makes sense. And then we take grams, and then we take 0.045 grams, and you take away the pulling power that you already have, which is your 0.24 sodium chloride equivalent, and you find that that is 0.0426 grams, and then that is 42.6 milligrams of sodium chloride that you have to add to this. All right, so let's go to number 13. Calculate the effective quantity of grams of sodium chloride in 100 milliliters of an intravenous fluid labeled 5% dextrose in 0.45% sodium chloride. Indicate whether this solution is isotonic, hypertonic, or hypotonic. Hyper, blah, blah. So, oh, no, wrong way. All right. I'm going to insert a little bit more space. We're going to need the room. Okay, so 13. So the first one is we have 5%. So we're doing 100 milliliters. We're going to find 5%. We're just going to assume, that we know where, I believe it doesn't give you the amount. Oh, no, it does. It does give you the amount. Okay. So you find that there's 5 grams in your solution of the dextrose, and then you want to find the amount of sodium chloride, which is 0.0045, which is equal to 0.45 grams sodium chloride. And now you have to find the equivalent. So you take your 5 grams, you multiply it by your E value, which is 0.18 E, and that equals 0.9, yeah, grams. And then you take these, and that is your sodium chloride equivalent. And then this time you're not taking it away, you're adding them together because they're both there. So we're going to take these two together. So that's 0.45 plus 0.9. You find that that is equal to 1.35 grams, but this is in 100. You find that that is over 100 milliliters, so that is equal to 1.35%. This is much larger than your 0.9% sodium chloride. So this is hypertonic. Hypertonic. Okay. So why would you ever need a hypertonic or a hypotonic solution? I know there is a couple of times where you will need a hypertonic solution. So a hypertonic solution like this could be used in a patient who is bleeding into the brain. That is also one. There are also situations where you want to save somebody's brain and they are just having fluid not draining properly, and you can do a hypertonic solution like this. This one's not too bad. It probably could be used, but I don't know if personally it's this solution, but this is like one of those situations where you would want to know the degree difference between this and your normal so that you can know how much you can get pressure off like the brain. That is a hypothetical situation where you might use stuff like this, but I'm not quite sure. I have not. I kind of hit on some of that stuff, but I never actually got to see it, so I don't remember quite exactly. But this is a situation where you would use a hypertonic solution. Usually it's sodium chloride, though. So I'm wondering why they would have dextrose. Anyway, number 14. You can tell I'm tired because I'm talking about everything under the moon. Pretty sure there are probably people in Timbuktu who are upset about how much I talk. Ooh, yay, we're going to make cocaine hydrochloride. So we're going to make some some eye drops with cocaine at 6 grams, eukotropine, hydrochloride, which is 6 grams, and chlorobutanol, which is 0.1, and sodium chloride, and water. And they want to know how many grams of sodium chloride. I keep going that way. Okay. So we have to look up the E values for all this. So for the cocaine, it would be 0.6 grams. And then its E value is 0.16. Eukotropine. And then this is the E value. It's 1.8. I looked it up so you don't have to. No. And then you should look it up. You should learn how to read these tables and go cross-eyed because that table was very, very small print. Or butanol. And that's 0.1 grams. And then that one is 2,4 E value. And then H2, your water, is 30 milliliters. So, how much sodium chloride would you need? You would need 0.270 grams sodium chloride for your total isotonic solution, because I'm pulling that from the previous, like, 6 problems that we've been doing. So you need to multiply these two, and that's why I have them all set up like this, so I don't have to do much. It's 0.096 sodium chloride equivalent. And then this is 0.108 sodium chloride equivalent. And then this is, sorry, oh, that's really obvious. And that is also, and then add them all together. You find that that is 0.228 grams sodium chloride equivalent that we already have in the solution. So then we take that away to find out how much more that we have to add. And we find that that is 0.042 grams sodium chloride that needs to be added, which is the same as 42 milligrams sodium chloride. So oh, I don't have any room. Okay. Right. So 15. So tetracane hydrochloride We have 0.1 gram, then we have zinc sulfate, which is 0.05 grams. Then we have to add boric acid and then water. And so we need to find out boric acid amount that we're adding. For some people on the last question may ask, why would you have cocaine? It's a pain reliever. It is a good topical pain reliever. If you're not snorting it, you probably won't get high. So if it's dissolved in a solution, and you're dropping like 2 drops in your eye, you're probably getting. I'm trying to remember what tropine does. Tropine, I believe, dilates your eyes, or it I can't remember. Man, I'm so bad at this today. All right, tetracaine is a cane. A cane is a pain relief as well. So you're like your lidocaine, and the zinc sulfate might be something for stabilizing. I wouldn't know quite what that is for, but this is 15, and so your tetracaine. I don't know how to spell. And then we have 0.1 grams. We need its E value. Its E value is, oh, I actually wrote down the wrong E value earlier. So hopefully I got the right E value now. Yeah, that table will make you go blind. And then we need 0.05 grams. And then its E value is 0.15 E. And then, all right, so then your boric acid, QS, but its E value is 0.52. We used this in a previous one. And then we are adding water, 30 milliliters. Okay, so that we know, because we've been doing this in like the previous 5,000 problems, that we need 0.270 grams sodium chloride when we're using 30. So we want to multiply these two by each other, and you find that this is 0.018 grams sodium chloride equivalent, and then this is 0.0075 grams sodium chloride equivalent, and you add these two together and you find that it is 0.0255 grams, and you take it from this, because that's the amount that you would need to take it to isotonic. So then, we're 0.0255 grams sodium chloride equivalent. You find that is 0.2445 grams, but that is your sodium chloride equivalent amount, but we need boric acid. So you take the 0.2445 grams, you divide it by your boric acid equivalent, and you find that that is 0.47 grams of boric acid. All right. We are done with 15. Now we are on 16. We're at the end of the page, guys. Yeah! Who would think I would get excited over math? It's sexy. No, it's not. It's terribly. And my Eeyore voice doesn't help it. Anyway, so 16. Homatropine, hydrobromide, 1%, for 15 milliliters. And then we have to make it isotonic with boric acid. And it's for the eyes. How many grams of boric acid? So this is a little bit different. Just take a minute. They aren't asking for grams. They already have the milliliters. And they just want to add some boric acid to it to make it isotonic. So why would this happen? Well, so maybe this is something that's stable on its own. I don't know. I'm just throwing out ideas. I don't know if that's true, but maybe it's stable on the shelf by itself. But you have to add that to make it, not degrade. Maybe the acid makes it degrade. But you need that acid to make it isotonic. So at the same time, so hydrobromide. So they want 15 milliliters. It is a 1% solution. So we find that there is 0.15 actual grams of this stuff in there. And then we have to find out how many how much sodium chloride or equivalents that we need to find. So to get it to isotonic. All right. And then, okay. Then we have to find the E value for homatropine, which is 17. So 0.17, sorry, 17 E equivalent. And then you have to take that number from up there, the amount, to find its equivalence in sodium chloride, which is 0.0255 grams sodium chloride equivalent. And then we have to take that away because we have to figure out. All right, so that is the equivalence of sodium chloride that we need. And then we have to convert that to boric acid. So to convert it to boric acid, we take 0.1095 and then divide it by 0.52, which is the E value for boric acid, if you remember correctly from, I believe it's the previous question. And find that is 0.21057 grams boric acid. That you would have to add to make this isotonic. All right, next one is number 17. Cool. All right, so procaine hydrochloride, it's a cane. So this is something to relieve pain. Sodium chloride, and then sterile water for injection. And then we want to make it to an isotonic solution, and it's for an injection. So any of the canes are, Yeah, they're not long-lasting anesthetics, but they are good anesthetics. So we have Procaine. We have 1 gram. Yeah, we have 1 gram because it's in 100. So it's 100 over 1 over 100 times 100. So you find that that's 1. And then you take its E value. ClE. All right, and then we have to find out the amount of sodium chloride, which is 100 milliliters times 0.009. What is equal 0.9 grams sodium chloride. All right, and then you take away the amount that you already have of pulling power that you have, and you find that you need 0.69 sodium chloride to add. Very, very simple one. Very, very straightforward. All right. So the next one is 20. So we have ephedrine, hydrochloride, chlorobutanol, dextrose, and rosewater. And this is for nose drops. So how much of dextrose should be used in compounding the prescription? So, all right, ephedrine. All right, hydrochloride, we have 0.5 gram. Its E value is 0.29 E. And then chlorobutanol, that is 0.25 grams. And then that is 0.24 is its E value. And then dextrose, and its E value is 0.16. And then that is a QS. And our rose, H2O, is 50 mLs. All right, so we're just going to multiply these two up here. So we find that this is 0.145 grams. This is 0.06 grams sodium chloride equivalents. And then you add these two together. That's 205 grams sodium chloride equivalents. And so you have to find out how much sodium chloride that we need. So 50 ml times 0.009 equals 0.45 grams sodium chloride. And then we have to take 0.45 grams minus the 0.205 grams, and you find that that is 0.245 grams of sodium chloride that would be needed to be added. However, we are not doing sodium chloride. We are doing dextrose. So you have to take the dextrose E value and divide it to convert it over to the amount of dextrose. We find that that's 1.53125 grams. I'm dexterous. Oh, what just happened? Okay. Next problem. All right, we are on 21. All right, so 21. All right. Naphthalene, hydrochloride, and sodium chloride. And then water, and it's 30 ml. Yay, we got back to the 30 mLs. Okay. So this one is to be used in the eye. How many grams of sodium chloride should be used? It says use the freezing point depression method. I'm not going to. I refuse. Honestly, I didn't notice that it said use the freezing point depression method. Well, I will show you how I found it without using the freezing point depression method, because I'm not crazy. All right, NaCl, QS. So this is 1%, so times 30 ml, and that is equal to 0.3 grams. Its E value, 0.3 grams times, where's its E value? I just had it in front of me. Oh gosh. All right, 0.27 is E value, 0.081 grams. And then we already know that 30 ml, and we already know this, but I'm going to write it out in case people have skipped ahead. And then I should write that. And then minus 0.018 grams. And you find that you need 189 grams sodium chloride. Freezing point depression method. Let me find my book. Because I'm pretty sure I can probably figure this out. So it'll just take me a second to find this in the book, because I have it bookmarked, because I'm a nerd. All right, so we have a table of freezing point depressions, and the freezing point depression change on this one is 0.16. And so the freezing point depression of sodium chloride is 0.58. So the equivalent, let me double check this. So the equivalent for this, let me find my calculator. If I'm, would it be 0.58 divided by what was that one? 1.6? No, that doesn't seem right. 0.16 divided by 0.58. Yeah, okay. So if you do the freezing point depression method, you find the e-value anyway. So you would find the e-value as 0.27. So you would take there's table 11.2 in the book. So this is from table 11.2 in the book. If you're doing the freezing point depression method, to find the e-value, which you take the change in temperature for 1%, and that change would be 0.16 for naphthalene, and then you would take the amount of change in temperature F 1% for sodium chloride, which is 0.58. For sodium chloride, you would divide the two, so you'd take 0.16 and divide by 0.58, and you would find that it would be 0.27 E. So it's the same here as here. So that's really the only difference, is you're just adding an extra step, which is why I said, this is nuts. I don't want to do it. But yeah, now you know how to do it, but doesn't mean I want to. But now you know that I know, and that you know I know, and that we all know that I know. It's great. And we can all revel in our knowing of knowing things. Okay, number 22. I hope it doesn't say something. Okay, good. None of them are asking you to do it with the freezing point depression method, because it's dumb. Well, it's smart, but it's like, I have the e-value. Why would I? All right, oxytetracycline, hydrochloride, and chlorobutanol, and sodium chloride. And we're going to add water, and we're going to do an eye drop, and how many milligrams of sodium chloride can be used in compounding the prescription. So this is a tetracycline. So tetracycline is one of the cycline antibiotics. Let me add some spice. Add some spice. All right, so this is 22. Sorry you guys have to deal with my really bad handwriting. Oxytetra. And that is 0.05. And its e-value is 0.12 E. And then chlorobutanol, 0.1, and then its e-value is 0.24 E. And then we're going to do NaCl, QS, and then H2O, 30 milliliters. Okay. So we got to find, so we know that that is 0.270 grams, because it's, well, actually, let me undo this. So this is 30 ml times 0.009 equals 0.270. So, and then these, we have to find out the equivalents. So this first one is 0.006, and then this one is 0.024 grams sodium chloride equivalent. Why do I, geez. I cannot do parentheses today for the life of me. All right, and then we add these, and that becomes 0.03 grams. And so take that away from your sodium chloride, and you find that that is 0.24 grams that I need. Oh, okay. So you need that much sodium chloride. All right. Next problem. So probably one of my favorite songs that I have been listening to on repeat is the original Black Panther cartoon show from BET, and the opening song is "Prepare for the Black Panther is Coming." It's amazing. If you have time to listen to it, I am listening to it right now, and it is pumping me up to do math problems at 2 in the morning. Okay, so this next one is a multiple choice question, and I got close, so we'll just go with it. All right, so number 23, phenocane, it's another cane, and the phenocane is a 1% solution. There's chlorobutanol, which is a 0.5%, and then it is in 15 milliliters, and then we have sodium chloride, QS, and then we have 15, I think it's 15 milliliters H2O. Yeah. All right, so 15 ml to figure out how much we have of this stuff in here, which is 0.15, and this is 0.75 grams. And then the value of phenocane, oh, that was procaine. Phenocane is 0.20 E, and that is equal to 0.03 grams. And then this is 0.24 E. And that is 0.18 grams. And so our NaCl is 15 times 0.009 is 0.135 grams. And then we have to take away 0.03 grams plus 0.018 grams. And that is equal to 0.087 grams. And we have to choose the closest thing. And if I remember correctly, 135 minus 87, and then 96 minus 87. Yeah, so this is 48, and this one is like 9. My brain is, yeah. So this one is the closest of the bunch. So we choose D. So we go. 24. So 24, the e-values are not in your book. So you have to go find an MSDS, and you have to go find these, which is annoying, but it's a learning experience that I didn't learn. Vincent looked up these for me because I was lazy. Partially I was lazy, and second off because I couldn't find the dibasic sodium phosphate. I found the first one, the monobasic. Monobasic's really easy. It's up on Wikipedia. So the monosodium, or what is it? Why did I say? Yeah, monobasic sodium phosphate. And then there's the dibasic sodium phosphate. So this one has 5.6 grams. This one has 2.84 grams. And then the E-value for this one is 0.49 E. And this one is 0.53 E. And so this one is 2.744 grams sodium chloride equivalent. And then this is, what is it? Okay, 1.5052 grams. Sorry, I smacked my lips into the mic. Did not mean to do that. All right, and then we have to find out the sodium chloride equivalent is 1,000 milliliters times 0.009 is equal to 9 grams is what we need. And so you take 9 grams of sodium chloride needed to make it isotonic, which is its pulling power minus the 2.744 plus the 1.5052. And we find that the amount that we need and so that is 24. All right. 25. Getting towards the end of our selected problems today. Okay. 25. All right, so we have ephedrine sulfate. And that's going to be 0.5%. Oh, sorry. I didn't mean to. Sorry. So how many grams of anhydrous dextrose should be used in preparing 1 liter of 0.5% of isotonic ephedrine sulfate nasal spray? Sorry, I meant to get in there that we are doing number 25. Sorry, I was a little bit too much on the gun. I wanted to. So we have anhydrous dextrose, and that is a QS, and then we're adding water. All right, so we need to find out how much, and that should be 5 grams, and then that's its E value is 2.3, and so then that is 1.15 grams. Okay, and QS, this one is 0.18 E. And so then we have to find out our sodium chloride amount that we would need to make it so that is our sodium chloride amount equivalent that we would need total in this solution. And so we take our 9 grams of sodium chloride equivalent and take it away from our ephedrine sulfate equivalent, which we would find is 7.85 grams that we would need of sodium chloride equivalent, but we don't need sodium chloride, we need dextrose. So we take 7.85 grams and we divide it by 0.18 E, and we find that we need 43.61 grams, and this is a repeating one, of dextrose. Cool, we got it. All right, all right, all right, all right. Okay, so number 28 is next. Let's go down to 28. All right, 28. Determine if the following commercial products are hypertonic, hypotonic, or isotonic. So we have an ophthalmic solution containing 40 milligrams per milliliter of cromolyn sodium and 0.01% of benzyl alkylonate chloride in purified water. So let's convert both of these to the amount of grams per 100 milliliters because that makes it easier for me. So that's the first thing that I want to do if I saw this problem. Let's just assume that we have 100 milliliters. So we're going to take that, and that we find that that is, in fact, 4,000 milligrams. So that is 4 grams for 100 milliliters, which is the same as 4%. Okay, so you follow me? So we're going to go back to this one. So 4 grams times its E value of 0.11 E, and that is equal to 0.044 grams sodium chloride E. Okay, and then our 0.01%, so our 0.01% is the same as that is the same as 0.01 grams for 100 milliliters. So 0.01 grams times its V value, which is 0.16 E. So we find that this, when we add them, well, actually, let's just do it this way because you guys. So this is 0.4416 grams. So our isotonic for 100 milliliters, will be 0.9 grams. So this is much, wrong way. So this is, for our isotonic, it's much higher than what we had. So this is hypotonic. All right. So now we go to part B. Part B is not nearly as complicated. This just looks really, really complicated. It's not. So part B was a parenteral infusion solution containing 20% weight per volume of mannitol. So that would be the same as 20 grams for every 100 milliliters. So we're going to take 20 grams times 0.18, and that equals 3.6 grams. which is the same as 3.6%. 3.6% is greater than 0.9%. So this one is hypertonic. This is hypotonic. This is hypertonic. And then C is a 500 milliliter large volume parenteral containing D5W, which is 5% weight per volume of anhydrous dextrose in sterile water for injection. So when we get into compounding lab, we get to deal with this all the time. So 5 grams is the same as 5%, and then its E value is 0.18. So it's 0.9 for every 100 ml. See, because this is for every 100 ml. So 0.9 is equal to 0.9. So it is isotonic. Cool. Do we have this, people? Do we know what we're doing now? Can we party with the big kids now? All right. So 29, let me, gosh, my handwriting is awful today. All right, so 29. For agents having the following sodium chloride equivalents, calculate the percentage concentration of isotonic solution. So we have 0.9% for an isotonic NaCl, and then divide that by 0.2, and that equals 4.5. And then B, what did I do? All right, B is 0.9%. You divide it by 0.32, and that equals 2.8125%. And then C is the same thing. All right. There you go. Those are the problems that we had to do, except for number 5, because number 5 I have to go and double check. But I wish I had gotten this done earlier. I'm sorry I didn't get it done earlier. Alrighty. So have fun. I'm gonna sign off. Good night.